Good day, everyone. Today, we will discuss friction in statics. Friction is a force that resists relative motion between surfaces in contact. Understanding friction is important because it affects the equilibrium and performance of many engineering systems. Objective: in this lecture, we will study dry friction, analyze equilibrium involving friction, and examine practical applications such as wedges, screws, belts, bearings, and rolling resistance. Dry friction occurs when two solid surfaces are in contact without lubrication. Friction always acts tangentially to the contact surface and opposes the tendency of motion. There are two main types of friction. Static friction acts when there is no relative motion, while kinetic friction acts when sliding occurs. As an external force increases, the friction force increases until it reaches the maximum static friction. Once slipping begins, the friction force decreases to the kinetic friction value. This slide presents the key equations used in friction analysis. The maximum static friction is equal to the coefficient of static friction multiplied by the normal force. Similarly, kinetic friction equals the coefficient of kinetic friction multiplied by the normal force. The friction angle is related to the coefficient of friction through the tangent function. An important observation is that friction is generally independent of the apparent contact area and depends more on the materials and surface conditions involved. Problems involving dry friction. When solving friction problems, we usually classify them into three categories. The first is when there is no impending motion, where only equilibrium equations are required. The second is when motion is impending at all contact points, and friction reaches its limiting value. The third is when motion is impending only at some contacts, requiring multiple solution attempts. The most important step is drawing an accurate free body diagram before applying equilibrium equations and friction relations. Wedges. A wedge is a simple machine used to amplify force. By applying a relatively small force, a wedge can generate very large normal forces. However, friction significantly affects the force required to move the wedge. In some cases, friction can be large enough to prevent motion entirely, creating a self-locking condition. Therefore, friction must always be considered in wedge design and analysis. Frictional forces on screws. A screw can be modeled as an inclined plane wrapped around a cylinder. The lead angle determines how steep the thread is, while the friction angle represents friction effects. To raise a load, additional torque is needed to overcome friction. In some screw systems, friction is beneficial because it creates a self-locking mechanism that prevents the load from moving downward when the applied torque is removed. Frictional forces on flat belts. Flat belts are commonly used for power transmission. The tension on the tight side of the belt is always greater than the tension on the slack side. The relationship between these tensions depends on the coefficient of friction and the angle of contact between the belt and pulley. Increasing either the friction coefficient or the contact angle improves the belt's ability to transmit power without slipping. Frictional forces on collar bearings, pivot bearings, and discs. Friction creates a resisting moment that opposes rotation. The magnitude of this frictional moment depends on the normal load, the friction coefficient, and the geometry of the bearing. Engineers use these equations to estimate power losses and ensure reliable operation of rotating machinery. Frictional forces on journal bearings. Journal bearings support rotating shafts under lateral loads. The friction force acting between the shaft and bearing surface generates a frictional moment. For small friction coefficients, the moment can be approximated using a simplified equation. The concept of the friction circle is often used to visualize how friction. Rolling resistance.
Rolling resistance differs from sliding friction. It mainly arises from the deformation of the wheel and the supporting surface during rolling motion. Because of this deformation, additional force is required to keep the object moving. Reducing rolling resistance is important in transportation systems because it improves efficiency and reduces energy consumption.
Conclusion. Review. To summarize, friction is an essential factor in engineering analysis. Correctly identifying the direction and magnitude of friction forces is critical for solving equilibrium problems. Free body diagrams, equilibrium equations, and friction relationships are the main tools used in friction analysis. Understanding these principles allows engineers to design safer and more reliable mechanical systems.